with the basics on how is it that we are going to be writing exponential functions. So here is my equation. For an exponential function, I know that I have an f of x equals a b to the x. Okay, so we're going to start by actually learning the names of what each one of these letters stand for. So very fast, we're going to start with A. A is what we call the initial value, and B is what we call our rate, or it can be our growth, it can be our decay, but B is going to represent the rate. So again, A represents the initial value, B represents the rate. So now we are actually going to see how is it that we can identify both of them, either the initial value or the rate. So first we're going to start with the initial value, A. The initial value is represented by the letter A. Now here we are going to start by seeing how can we identify the initial value in different places. So we're going to start with the graph. The initial value A in a graph can be represented by the y-intercept right here. So A, I know that it means initial value, but also we must remember that the initial value is the same as the y-intercept. So in this case, A equals -1. So even if I want to get technical about this, I already can start writing my function as f of x equals -1 b to the x. So I know that we haven't talked about b, but so far that's what A is represented. So let's look at another example. Here I have a decay model. So no longer we have a growth, we have a decay. So is that going to change who represents my A value, my initial value? Not at all. In this case, A is still going to be representing the initial value. And again, let's not forget that the initial value is the same as the y-intercept. So in this case, this will be my initial value. So A would be equal to 3. So if I want to get technical, I can start already writing the equation for this graph as f of x equals 3, because I already know that's the initial value, bx, and we're going to talk about that in a minute. So far we know that A, like I said, is the initial value, is representing, is another name for us to call the y-intercept, and it's this point right here. Okay, now we're going to start talking about the B value, the rate, this number right here. Now, this number, we need to understand something. This number, thanks to the B value, is what is going to decide, or where we can tell if what we have is going to be a growth or is going to be a decay. Okay, so let me give you an example. B is my rate, okay? So B is my rate. If my B value is any number bigger than 1, I'm going to have a growth. Example, if I have, let's say, f of x equals A, just to say any number, and then I have a number 3 to the x, this is going to be a growth just because of that number right there. To give you another example, if I have f of x equals just A, to say any number, and then I have times, let's say, a 1.5 to the x, this is going to be growth just because this B value is bigger than 1. Versus having a number less than 1. And by less than 1, we mean a number between 0 and 1. So for example, B is still going to be my rate. But if my rate is any b value that is greater than 0 but smaller than 1. So between 0 and 1, we are going to have a decay. So let me show you an example. Let's say that I have an f of x equals, and I'm going to keep an a to say any initial value, times 0.5 to the x. Just because this number is between 0 and 1, we are going to have a decay. So let's give you another example. What if I have an f of x, and one more time I'm going to use a to say any initial value, times 1/4 to the x. So again, it does not matter that I have a fraction. If my number is between 0 and 1, I'm going to have decay. So here we have an example when we are going to be changing our b value and our initial value is 2. We can see the y-intercept right there. So what I'm doing is I have a 1.1, but I'm going to be increasing it. As I keep increasing it, I notice that I still have an exponential growth, and it starts getting steeper and steeper. 1.4, 1.5. Every time I go above 1, I keep getting growth. But if I go in the opposite direction, if I get 0.9 or 0.8, I'm start getting more a decay, even though that my y-intercept in my initial value is still 2. That doesn't change. So any number below 1 is decay, and any number bigger than 1 will give me a growth. Okay, so by now we already talked about a being my initial value. We talked about b and how b can change my exponential to be a growth or a decay depending on its value. If it's bigger than 1, it's a growth, and it's between 0 and 1, like any of those two values, 1/4 or 0.5, we will have a decay. Well, now we're going to focus on how is it that I can build. Now I know how to find my initial value. But how is it that I can find or put together my b value, okay? And here's where things get a little more complicated. What does that mean? Most of the problems that we're going to talk about are growth or decay. Both of them are going to be given to us as a percentage growth. So the first step that we're going to have, according to our problem that it's going to be given to us, we're going to have to identify if what we have is actually going to be a growth or a decay. Why? Because each one of them have a different formula. The formula is very similar. It's changing between a 1 plus r if it's growth or a 1 minus r if it's decay. So, in other words, if I happen to know that my problem is representing growth, I'm going to use this formula. If I happen to know that my problem is talking about decay, I'm going to have to use this formula. What I don't want you to lose track is that this right here, that's 1 plus r, and this 1 minus r is actually what my v value is. It's just that I put together my b value depending on if I have growth or decay. So here I have an example. An iPhone approximately costs $750 each year. Its value decreases about 25%. What would be its value 3 years after its purchase? Okay, so this we know that is going to be an exponential decay. Why? Because the decreases that they're talking about in my problem, this decreases, they talk about that each year is going to be at 25%, which means even though there is always 25%, it's not the same. Because the 25% of the first year's value is going to be more than the 25% of the second year's value. So it will be changing. So we're going to start losing, our iPhone is going to start losing a lot of value the first years, but then it's going to start losing less value the older it gets. It's going to be a little more stable if you want to see it that way. So first of all, I know that I have a exponential function. So I'm going to use my f of x equals a b to the x. Okay. Now, since we are talking about decreasing, I know that I have to use my decay formula. And what's going to be my decay formula? F of x equals a times 1 minus r to the x. So, first of all, let's start with the easy part. The easy part is that to identify my initial value. What is my initial value? Right here, the 750. So I can already say then my f of x would be equal to, instead of a, 750. So now I need to build my b value, okay? So here's where you're going to have to do something a little bit different. So I'm still going to have 1 minus, and then I need my r value. Be careful here. This is a very common mistake. I have a 25%, right? But for me to write it here, I cannot write it as 25. That is a percentage. I need to change the percentage into the decimal form. So if you don't remember that, 25% is 25 over 100, which is the same as 0.25. So that means that here I'm going to say y minus 0.25. That would go to the x. So we can start building now our equation, which is going to be f of x equals 750 times 1 minus 0.25. It'll be 0.75 to the x power. So this is the equation of the problem. But now we have to pay attention because the actual question is asking what will be the value after 3 years. So what does that mean? Then my x value would be a 3. So that would look this way. It would be f of x equals 750 times 0.25. And this 3 years later, so x is 3. We put all this in our calculator and the answer would be $316.40. So that means that if today you buy an iPhone, which is $750, 3 years later, the same phone will cost $316.40. That's the way it would go. Let's do one more example, okay? So we have, in the year 2000, the world population was approximately 6.08 billion people. The population growth rate is about 1.25% per year. What would be the estimated population by 2025? Okay, the first thing that we need to do before we start writing our equation is identify what kind of exponential behavior we have. And this one is an easy one because it's actually saying growth right there. Okay, so now we're going to start by identifying our initial value, which we know that the world population in the year 2000 was that. So that's where I'm starting at, 6.08 billion. Okay, so if this is going to be a growth, my equation is going to look as f of x equals a times 1. Since it's growth, it'll be plus r to the x. Okay. So I know that my growth is my initial value is 6.08. So I'm going to say f of x equals 6.08. That's my initial value. Okay. And then I have growth. So I'm going to say 1 plus r. But be careful. One more time. My rate is giving us a percentage. So I know this is going to be 1.26%. But I need to change it into a decimal For those of you who don't remember, this will be 1.26 over 100. And that becomes 0.0126. Okay? So it'll be 1 plus 0.0126. That will be to the x value. Okay, so now my equation is f of x equals 6.08 times 1.0126 to the x. So this will be the equation for the problem, but I'm being asked to make a prediction by 2025. So we started at the year 2000 and now we go to the year 2025. So that means 25 years later. How is my equation going to look like then? F of x equals 6.08 times 1.0126 to the 25th power. We put all this in our calculator and our answer will be f of x equals 8.314. That means that the population in 2025, it is estimated to be at 8.314 billion people.